In this example, we'll learn how to use the Exalinks software by taking a logic circuit we've seen before, exclusive OR, and converting it into an Exalinks project. The exclusive OR gate that we've looked at before has 5 constituent gates, 2 inverters, 2 AND gates, and 1 logic gate. It also has 2 inputs and 1 output. So how can we implement this using our design tool, specifically the ISE WebPack? Let's take a look. Once we launch Exalinks in the ISE WebPack, we're presented with this. This is a development environment that requires a project, so we're going to go into the File menu and choose New Project. The dialog that comes up asks for a project name, and I'm going to call this Example XOR. Make sure you put this in a location for which you want the files, and make sure the top level source type says HDL. Next, we're presented here with the different properties of the device we want to use to simulate this particular model. The values I have here are what I'm going to use for all the examples I show you of HDL. You'll notice here I'm using the Spartan 3 family. The device is XC3S50, and down here the synthesis tool is VHDL Verilog, and I'm using the ISE simulator. Hit next. Here we can create a new source file. By hitting the button that says New Source, I can choose a Verilog module, and I can give it a file name. Now I'm going to give it the same name as the project, Example XOR. The location by default is wherever you created the project. So hit Next, and here I can specify my input and output ports, what in Logism we called pins. In our Logism model, we have 2 input pins and 1 output pin. So here I'm going to create 2 ports to serve as our input pins. And I'm going to keep the names simple as A and B. And I'm going to call the output pin C. Now here I do need to switch this direction from input to output. And you'll notice there's a third option there, in out, that we're not going to have to worry about here with this example. So I hit Next, and I'm presented with a summary of the different ports, and I hit Finish. Now you may get this message as well. Just say yes, you would like to create it. And now we're back at our wizard. I'm going to hit Next. If I had any existing Verilog HDL code, I could import it through this screen, but since I don't, I just hit Next, and I'm presented with a simple summary of the project, so I hit Finish. And in doing so, a few things happen. One is we're presented with this design summary, and over here on the left you see a couple of tab windows which have now filled. The top shows you the sources. Right now we have one source, and that is the Verilog HDL file that I specified during the wizard. It also appears down here as one of the tabs, Example XOR.v. That's where I want to be. This shows the stub code produced by the ISE WebPack for the Verilog HDL. The time scale by default is 1 nanosecond over 1 picosecond. And down here at the bottom we see the actual Verilog HDL code. And we see 2 inputs, one called A, one called B, and 1 output called C. It also adds some comments here that you can fill in as much as you'd like, perhaps with your name. But you'll notice as we go that there are some similarities with the C++ language you will have encountered in CompSci 121 or CompSci 201. You'll notice semicolons at the end of each statement. You'll notice that some things are colored different colors, such as blue for keywords and green for comments, like you may have encountered in CompSci 121. What we're going to do here is add a little code. what I'm going to add is code to implement the logic that I want for this particular circuit. Now, looking back at our logism circuit, we have 2 AND gates, an OR gate, and 2 inverters. What I have to do is take this setup and convert it into the Verilog HDL syntax. Now, that syntax is very much like what you will have seen in C++. What I'm going to do is assign a value to the output, but the value is going to be a Boolean expression. And I'm going to use, again, things that you will have seen before. This assign statement assigns the Boolean expression which implements the exclusive OR circuit. As you can see, we notice the AND operator is the 2 ampersands, the OR operator is the 2 vertical lines, and the exclamation point serves as the NOT operator or the inverter. Again, all similar to what you will have seen in C++. Now, this is all I need to do here. So what I'm going to do is check my syntax. Over on the left, we see a bunch of different options here under processes. Here we see synthesize, XST. I'm going to expand that a bit. And one of the options is to check syntax. If I right click and choose run, it will of course remind me that I do need to save, so I'll do that. And we wait, and you should see your cursor spinning, indicating it's working. And what it's going to do is it's going to check the syntax that you have to make sure that what you're doing is actually valid Verilog HDL. Now, depending on your system, depending on what you're doing, this may take different lengths of time. But what we're going to end up with is information here at the bottom that will tell us whether or not our syntax is correct. And if it is, then we can move forward and do a little more design work. As we can see at the bottom here, there were no errors in compilation, and the process completed successfully. You also notice here on the left that there's a circle with a check mark. This green circle with the check mark indicates success. Something else that it also did was it created a schematic for us. The option here, View RTL Schematic, if I run that, it will produce some output down at the bottom, but it will also produce a schematic diagram of the circuit I'm trying to create. First, at a high level, and if I double click on this, it'll drill down a little bit farther. And again, if I double click, it'll drill down to the circuit, to the gates that we're used to from logism. Now, if I want to go backwards, I just double click outside the gray box and do it again, and it will take us back to the original. So you could drill down to various levels, and that's kind of handy, especially if you're building a complex circuit. Now that I have the Verilog HDL for the circuit, one thing I want to do is I want to test this out. So what I need to do is create a test bench. Some people would also call this a unit test, which is a keyword from, or keywords from computer science. However, excuse me, what I want to do is create this test bench, which is really just Verilog HDL code. So I go back over here to the left and click on Sources. And up here at the top, you'll notice Sources for. And what we've been doing is synthesis and implementation. What we want is to create a source for behavioral simulation. So I change that option. I click here on the XC3S50 and I right click and I choose New Source. What I want here is a Verilog test fixture. And I'm going to call this, let's see, using sort of the book's notation, I call it test underscore and then what it is I'm testing, example XOR. I do want to add it to my project, so I leave that checked. When I hit next, it asks me which source to associate it with. And since there's only one, the choice is obvious. I get a summary and I hit finish. And when I do this, it auto-generates some Verilog HDL code. And you can scroll through it. And right now, what we want to concentrate on is the fact that this set of code creates one of our circuits so that we can test it. Now, this section here, beginning with the word initial, is what's going to allow us to play with the inputs so that we can see how the output develops. Now I'm going to add some code here where the comment says add stimulus here. What happens is initially we set our input ports A and B to 0. We wait 100 nanoseconds and then we can do some other things. Here's what I'm going to do. I want to test this in a couple different ways. So I'm going to set A to 1. I can't forget my semicolon. I'm going to set B to 0. And then I'm going to say, okay, wait 50 nanoseconds. The pound 50 indicates a delay of 50 nanoseconds. And then I'm going to change the values. I'm going to leave A at 1, but I'm going to set B to 1. And again, I'm going to say wait 50 nanoseconds. And then finally, I'm going to set A to 0 and B to 1. As the last step, I delay again, 50 nanoseconds. And I'm going to add this statement here that says $finish, which will end the simulation. Now I've written some Verilog HDL code, so I want to check it out. Over here on the left, excuse me, you see, if I click on my file here, down here at the bottom it says Exalinks ISE Simulator. If I expand that, I have two options. The first is check syntax. I want to do that first. So I right click and run. Of course I forgot to save, so I need to do that. But as it goes through and it's going to compile this code, make sure that the syntax is correct, I shouldn't have any problems here. What I'm doing here is very basic, nothing complex. So I shouldn't have any problems. You can do all sorts of things in here. You can have if statements, you can have different types of delays, you can do all sorts of things. We'll explore this a bit over the course of the semester. Again, depending on the system you have, depending on how many windows you have open, etc., this may take different lengths of time. And now it's checking the syntax, and the green circle with the check mark indicates everything is fine. The next step is to simulate the model. If I click here on Simulate Behavioral Model, right click and say Run, here's where the simulation is going to come into play. An interesting side effect of this is you often get this message. Say no to this message when you do see it. Now you get some feedback here about how long the simulation ran, things like that. Over here, there's a tab that says Simulation. If I click on that, I see a timeline up here at the top in nanoseconds, and I see the waveforms for both the two inputs and the output. Now the output here, C, is on the top. And just to compare what, to get an idea of what we were doing, going back to our initial test bench here, the initial set of conditions after 100 nanoseconds was that A was 1 and B was 0. And that would go on for 50 nanoseconds. If we look back at the simulation, here's the timestamp for 100 nanoseconds. You'll notice that A moves up to 1 while B remains at 0. But for these 50 nanoseconds, because A is 1 and B is 0, you see the output is also high. The output is also 1. Now at 150 nanoseconds, that changes. It goes back down because we switched the conditions. at 50 nanoseconds here, 150 nanoseconds, both A and B are high voltage. As a result, with the exclusive OR function, C, the output, becomes low. And you can plot that over time. If you right click, you can zoom in to get a more discrete visual of the time. And this is the kind of thing that can show you how the circuit reacts to different inputs, using the test bench, setting delays, and seeing to make sure that works. Now, I'm going to go back to my test example code here. I'm going to make sure I have everything saved. It looks like I do. And at this point, I could play around with the test bench a little bit more, try some different cases, try some different conditions. But I'm satisfied that the exclusive OR circuit that I've created works. If I want to go back and change that circuit in any way, I change up here the sources from behavioral simulation back to synthesis and implementation. At this point, I have access to my original circuit code. I can modify it. I can once again check the syntax, check the schematic, basically make any modifications that I want to make. At this point, I'm satisfied, so I'm going to close the project. And if I want to, I can create a new project, or I can simply close the application.